talking dots, I can see them.
What?
The red dots on the left. It's
Again?
there's a red sign on the left shows that it's recording, so you don't need to go.
Okay, today I will develop this test for testing the significance of whole model. And to do that, I need an expression for, what's wrong? I need an expression for SST, SSR, SSE. And the equation that will lead us to the formal test is this equation. This is the fundamental equation that will lead us to develop a test for testing this hypothesis. Now, in this equation, we have SST, we have SSR, and we have SSE. First, I will develop the simplified expressions for all three of them because I'm going to use the three of them in developing my test statistic. So I start with SST, which I wrote on the right side of the board. We started this SST with the amount of variation in Y, the total variation in Y, and we started with this expression. Regardless, your model is simple or multiple regression, there is only one Y. So the total variation in Y, the formula doesn't change. It's the same formula. You want to write it in matrices or you don't want to write in matrices, it's up to you. The simplified form for this one is summation of yi square minus summation yi whole square over n. The only thing I can write in terms of matrices is this summation yi square. You can also find it from the matrices by using this formula y prime y. The other one, I can write it in terms of matrices, but that will rather overcomplicate the things instead of making it more simple. So better you find that component without matrices, the summation yi whole square over n. That component should be found without. Even the first one, I prefer it to be without matrices, but this is the way I can write it in terms of matrices. Y prime y will give us actually summation yi square. Why? Because y prime is what? It's like this, y1, y2, all the way up to yn. This is the transpose of my vector y. And then vector y will be what? y1, y2, all the way up to yn. If I multiply these two, what do I get? I do get summation yi square. And same is true for e prime e. If I multiply e prime with e, I get summation ei square. So this is the simplified version of SST. Then I start talking about SSE. We know the formula of SSE comes from the name of SSE. SSE is what? Sum of squares of errors. So it's the sum of squares of errors. This summation ei square can also be written as e prime e with the same spirit as I wrote y prime y as summation yi square. Now to simplify this expression, I'm going to put this definition of e into the equation, and this is y minus x beta hat. So e is y minus x beta hat. E prime will be y minus x beta hat prime times y minus yes, y is a vector, x is a matrix, beta hat is a vector. Yes, all of them are vectors and matrices. So in bracket is e, then prime, and then I have e. Clear? Now when I do apply the transpose, what is a minus b whole transpose? A minus b, not a multiplied by b. First, I'll apply it on two terms. There is a minus b whole transpose. It's simple, a transpose minus b transpose. The order reverses when it's the product, a multiplied by b transpose. So the first thing I do is it's y transpose minus x beta hat whole transpose. This is the first thing. Clear? Now talk about the second term in the first bracket, x beta whole transpose. When I take the transpose, it's a product, the order will They will change. So it is Y transpose minus beta hat transpose times X transpose. Clear? Now it's a 2 cross 2. 2 elements in the first bracket, 2 elements in the second bracket. I will multiply it. As I do multiply, I will get resulting 4 terms. Yes.
So the transpose of something multiplied by this something does it have any formula or something?
I used this expression A minus B whole transpose equals A transpose minus B transpose. Then I used AB whole transpose equals B transpose into A transpose.
Yeah, but I mean, if we have X transpose multiplied by X, will that give a specific thing or no?
Of course, it will reverse.
It will reverse to be what?
Again, X transpose times X.
So this is what will happen here because this is Y minus
We will
X.
see. I think you're talking about one step ahead.
No, I thought there's an identity of something. We can just put it in one step.
Are you
Because
talking about after multiplying it with X beta?
No, the first thing is something transpose multiplied by this same thing, right?
Yes.
So what is the identity when we multiply the transpose by?
No, the inverse. You are confusing the transpose with the inverse.
So there is no such thing.
No. There is no such thing with the transpose. E inverse times E is identity.
Yeah. Okay.
Yeah. You're confusing it with the inverse. Inverse is different. Yes. So now I have 2 terms in the first bracket, 2 terms in the second bracket. Straight away I will multiply them and I'll get what? I'll get Y prime Y first into first term. Then I'll get minus beta hat prime X prime times Y. This is the second term. Then I have Y transpose times X beta hat. And the last one will be plus beta hat prime X beta hat. Is it clear? Yes. It is simple 2 cross 2 multiplication. But when I'm doing it with matrices, I need to be careful about the order. If beta hat is in front, it should be in front in the product also. So the first term, I cannot write it Y times Y transpose. It should be Y transpose times Y. Now tell me what is on the left side? SSE, summation EI square, correct? Or E prime E, any of these three. What is the order of that thing? E prime E or SSE or... It's a 1 by 1 single quantity, correct? Assuming that you know that the left side is 1 by 1, what will be the order of these 4 things? All of them should be 1 by 1. Otherwise, the equality will not hold. All of them should be 1 by 1. And it is correct. All of them are 1 by 1. Talk about them 1 by 1. What is Y prime Y? Summation yi square. This is 1 by 1. Talk about the next thing. What is the order of beta hat prime? Times X prime times Y. It should be 1 by 1. I will show it's 1 by 1. The third is 1 by 1. The fourth is 1 by 1. The thing I'm going to prove now is that these 3 quantities, they are all same. Not only their order is same, but the result is also same. So you have the same quantity 2 times in minus, 1 time in plus. The result will be 1 time in minus. 2 times in minus, there is minus, and there is 1 plus. So 2 of them will cancel out and you will be left with 1 of them. Before doing that, I will prove that all 3 of them, they result into same thing. So I'll start with the first one, which is what? Which is beta hat prime X prime Y, correct? Yeah, addition is only possible if they have the same order. Correct. We are doing addition or subtraction, right? The 4 terms are added or subtracted. It's only possible if all 4 of them are same. And again, equality is only possible if the left side order is same as the right side order.
So how do you know that all of them are 1 by 1? Maybe it's 1 by n plus 1 multiplied by 1 plus n by plus 1.
I said the overall this thing, overall this whole thing is 1 by 1 because it's, if it is not 1 by 1, you cannot subtract it from y prime y.
So the whole term, okay.
So let me put the definition of beta hat. What is beta hat? Where is it? There it is. So I'll put beta hat, take the transpose of this beta hat and put it inside. What will you get? The order will reverse. Y prime will come in front. Then I will have X prime. And then I will have the transpose of this symmetric matrix. What is the transpose of symmetric matrix?
Y prime.
Again?
Y.
Because there is beta hat prime.
Can
Yx prime, no X prime. You're correct. X times X transpose X whole inverse, finished, and I get back to X prime Y. Correct? Is it correct? Or I made some mistake?
beta head, just beta head, right?
It's beta hat transpose.
Beta head transpose.
Make this all the transpose.
Yeah, I have to make the transpose of all of this. I'm talking about the term in the bracket. There is beta hat transpose. There is transpose of Y, then the double transpose of X will be simply X, then the transpose of the symmetric will be the same thing, and then there is X prime Y coming from the same.
Y transpose, Y symmetric is
Again,
between bracket, Y is the same.
it's a symmetric matrix. This one is symmetric. This thing is symmetric. Even this thing is symmetric. I'll show you in the Excel file. This is symmetric. There is a result that the transpose of symmetric matrix is the same matrix. For example, if I have A, which is 1, 2, 2, 3, this is a symmetric matrix. If I take the transpose of A, it will be what? The same thing. So same is true for X prime X, and same is true for X prime X whole inverse. They are both symmetric. So we have result number 1. Now I'll simplify number 2. Number 2 is Y prime X beta hat. This is Y prime X. What is beta hat? Same thing. 1 and 2 are same things, correct? Then I'll simplify the third one. Beta hat prime X prime X beta hat. So my beta hat prime is this one, correct? So I'll take this one, Y prime X times X prime X whole inverse. This is beta hat prime. Then I have X prime X. And then I have beta hat again. If I look at this one, we can cancel, I think, 2 of them. We can cancel this part because it's the same thing, inverse times the same thing. So this will become identity, and identity will be merged either to the left side or to the right side, wherever you want. So as a result, I will have Y prime X times X prime X whole inverse times X prime Y. So you see the 3 results are all same. They are all same. So what I can do is I can cancel 2 of them, and the resulting SSE will be what? It will be Y prime Y. Let me first write the equation as it is, and then I will cancel. Identity is kind of 1 in matrices. So now I will cancel these 2 because I just proved that they are equal. So I'm left with what? Y prime Y minus beta hat prime X prime Y. Correct? Now, go back. What is your SST? SST is Y prime Y minus something. This minus something is missing there. Y prime Y is there, correct? I need to establish that relationship between SSE, SST, and SSR. So Y prime Y is there. We know that SST, here I'm going to write, we know that SST is Y prime Y minus summation Yi whole square over N. This thing is missing in the equation. So what I'm do is I'm going to add and subtract this thing to bring SST into the picture. So there will be Y prime Y. Here I subtract. And I add this thing also to balance the equation. Clear? Now, what is this? This is SST minus, I take minus common. So I will have beta hat prime X prime Y minus summation yi whole square over n. This is SSE. And we know that SST is SSR plus SSE, correct? We know that this should be SSR plus SSE, meaning SSE should be SST minus SSR, correct? Which means this thing is what? This is SSR. So now look at the right side of the board.
I think it's not the same.
Not the same. Where did I write SSR?
Third one.
Yes. Now it's actually SSE. It's SSE, this step, the top step, not the top, this one. Look at the top now. So now we have the expressions for all of them. Now that we have the simplified expression for the three of them, and these are here. SST, the direct expression is y prime y minus the correction factor. SSE is y prime y minus beta hat prime x prime y. SSR is beta hat prime x prime y minus the correction factor. Now, if, for instance, you are stuck with something, you can find, if you have two of these components, you can find the third one by taking the difference. You don't need to find the third one directly with the formula. If you have SST and SSR, for example, you can find SSE by this equation. These three are the direct formulas for all three of them. But if you want to save your time and you have two of them and you need SSR, just take SST minus SSE. That will be SSR. You don't need to put the things back into the original formula. Or if you have SST and SSR, you can take the difference between SST and SSE and you will get SSR. Now let us develop the spirit for the full test, F test. For testing the significance of full model, what is the hypothesis? The hypothesis is that all slopes are 0 against at least one of them is not 0. True? Now, to test this hypothesis, as I said, I'll be using this equation. Indirectly, what am I saying in H0? That the model is useful or useless? Useless. Correct? None of the variation in Y is explained by X's. Nothing is explained by X's. That's the meaning of H0. Useless. What is the meaning of H1?
At least one of the X's.
Some or maybe all. But at least some variation in Y is explained by at least one of the X's. Correct? Now, if your H0 is true, and none of the variations is explained by the X's, and your model is actually useless, what will happen to this equation?
SSE will be
SSE will be huge. SSR will be close to 0. None of the variations will be explained by your model. SSR will be close to 0. Close to 0. Towards 0, I would say. We'll talk about the aim later, because if yes, it's correct. But we'll talk about the aim later. Now, let us talk about the two extremes of this thing. The two extremes of this thing are, one of the extremes is that SSR is close to 0. In that case, your SST will be SSE, approximately. Correct? In this situation, you should be supporting H0 or H1. When your SSR is 0, when will SSR be 0? When there is no explained variation and the model is actually useless. So you should be supporting H0. So this supports H0. Correct? The other extreme. Let's talk about the other extreme. All the variation is explained and your SSE is close to 0. In that case, all the variation will be explained. Where should you support? You should be supporting H1, correct? Correct. So we developed a rough rule that if the value of SSE goes close to 0, we reject H0. We go with H1. A rough rule, right? A very rough rule. Or if SSR goes close to SST, also in that case, we reject H0. These two are the same statements. SSE goes to 0 or SSR goes to SST. These are the same statements. What if I define, instead of in a single quantity, I define as a ratio SSR over SST, not SST, sorry. I take them to another scale. Now, if SSR is 0, this ratio will go to what? 0, correct? This ratio will go to 0. And if SSE is 0, this ratio will go to what? Infinity. So this ratio, which is the ratio of two sum of squares, this can stay anywhere between 0 and infinity, where 0 supports H0, infinity supports H1, correct? Correct. Now the problem here is SSR has the different unit. It's coming from K predictors. SSE has the different units. As an example, if I have section 1 having 5 students in stat 310, section 2 having 20 students in 310, can I compare the sum of scores of section 1 with the sum of scores of section 2? I cannot compare. Why I cannot compare? Difference between the number of students, the scale is different. To bring them back to the same scale, what should I do? Divide by the number. Divide by the number from where it is coming, or in statistics sum, we call it degree of freedom. Divide by the degree of freedom from where it is coming and convert it instead of sum to average. This is a sum. If I divide them by the number from where they are coming, they will become the averages. And these averages are more comparable. Rather than the sums, averages are more comparable. This whole thing, we call it F statistic. From the same sample, yes. But they are sums. They are sums. To compare the two of them, we need to convert the sums to averages. Sums directly are not comparable. Averages are. So when you to bring them to the same scale, they are not at the same scale. For example, if I have a model with 4 predictors, right? SSR will explain the variation explained by those 4 predictors, the total variation explained by those 4 predictors. When you divide it by 4, what do you get? The average variation explained per predictor. So you will bring it to the scale of 1. Same is true for SSE. SSE is the total unexplained variation. So if you divide it by the number, the remaining number n minus k minus 1, it becomes the total unexplained variation per predictor. So they come to the same scale and they're comparable. Once they are comparable, then the ratio is meaningful. The ratio of the two is meaningful. Yes.
So why do we subtract one at the degree of freedom?
Why do we subtract 1 from the degree of freedom?
Yes, this is a question I've never got the answer to. Is there a proof or a logical reason?
I'll give you the proof. Not the proof, I'll give you the logical reason. Proof will not be helpful for you. I'll give you the logical reason, but this at this point it will confuse me. So later I will give you.
So we know that n minus k to get the same. As you said 5 series and 20, but d minus 1.
I'll tell you about -1. Yes.
Do we have to prove that SSR and SSE have chi-square distribution?
No, you don't need to. You have proven this in 301, I think. Have you?
Yes.
Not for SSR.
You have proven. I have. Don't forget. I have taught all of them. I have taught 301. I have taught 302. You have proven it in not in 301, I think. In 302. Chi-square comes in 302.
We are proving it now.
Yeah. Chi-square comes in 302. And then you will prove that the ratio of two chi-squares divided by the respective degrees of freedom is f. You will do that. But here you don't need to. Be clear. In this course, you don't need to prove that this is chi-square, this is its degree of freedom, this is chi-square, this is its degree of freedom, and the ratio becomes f. You don't need to. You need to use it. You need to know how to use this. You need to know that this ratio, this whole thing of f stays between 0 and infinity. Now, here is the scale of f. We are saying fail to reject H naught if the tendency of f is close to 0. And we are saying reject H naught if the tendency of f is towards infinity. Somewhere in between, there will be a cutoff point where you will say, if I'm beyond the cutoff point, I will reject it. If I'm before the cutoff point, I will not reject it. What is this cutoff point? We call in statistics this thing as the critical value. Why is it so critical? Because this is the one, the value is deciding whether you reject or you fail to reject. If you are on the right side of the critical value, you reject it. If you're on the left side of the critical value, you fail to reject it. Where does this critical value comes from? This critical value comes from the distribution of this statistic. And this statistic, which is SSR over K over SSE over n minus K minus 1, follows F distribution. And F distribution has two parameters. F distribution has two parameters. These two parameters are called V1 and V2, the degree of freedom for the numerator and degree of freedom for the denominator. The numerator degree of freedom for your case is the number of predictors. The denominator degree of freedom for your case is n minus K minus 1. So you need to do what? You need to go to the F distribution and get this critical value and compare the value of your sample with that critical value, or you can also define the p-value expression. Any of the two approaches will work fine for you. So what I'm going to do now is I'm going to open the Excel file and I'm going to show you how this test is applied. We will work with the same data set that we have been working with, which is what? The delivery time? Delivery time depending upon, yeah, this one, I think. Now focus carefully on the application part. Now everything for me is ready here. All of the things are almost ready. So let's say I use this space, or let's say this space. What I need for F statistic is what? Look here, the formula at the left. I need SSR, I need K, I need SSE. I need n minus k minus 1. Now SSR, do I have it? In the last class, did we find SSR? I will find it using the formulas I wrote there. I will find it today. I will also find SST. I will also find SSE. So let us start with finding SST. What is SST? Using that formula. So I'll use the matrix multiplication transpose of y. Yes, I have y, comma, with y. This is y prime y minus the correction factor minus sum of y whole square over, do I have n? Over n. No, I don't have n. Let me call it 25. So I have 5, 7, 8, 4. This is the total variation in y. 5, 7, 8, 4. Now, out of this total variation, did I add the formula for SSR? SSR is y prime y. So I'll copy it from here. Not y prime y. It's beta. What is it? It's beta hat prime. So let me copy the correction factor only. SSR is the transpose of this beta hat. This beta hat. It's here. SSR is here. Beta hat prime x prime y minus the correction factor. So I'll find beta hat prime multiplied by x prime y. Now look here. This is my beta hat. I'll take the transpose of this one, and this is my x prime y, which I used in calculating beta hat. So I'll take the transpose of this beta hat and multiply it by x transpose y minus the correction factor. So the transpose of beta hat multiplied by this thing, which is x prime y, and I multiply these two minus the correction factor, which I copied from the formula. So I have 5550. Now this should give you immediately an impression. What? The total variation was 5,784, correct?
Mhm.
How much is explained? Almost 5,550. Majority of it is explained, correct? So if I find the SSE by direct formula or by taking the difference, that will be around 200 and something. Is it?
Yes.
It will be around 200 and something. So what's the immediate impression? Are you rejecting? Are you going to reject H0 or fail to reject H0? You are towards rejecting H0. The earlier tendency of this thing is you will be rejecting H0. Very clear from these numbers. Yes.
Is there a specific measurement for?
At this point, just an idea, no specific or no exact measurement at this point. The exact measurement will come from the value of F. The SSR over SSE. The ratio is here. The ratio is here. Again?
SSA is not
SS
You
minus.
you divide it.
Where? Did I?
Yes.
233. Yes, correct. Now what? Now I'll find the value of F, which is SSR over how many predictors do I have in the model? 2. Over SSE divided by, what is my N? 25. What is my K? 2 minus 1. 261. Is it close to 0 or infinity? Of course, this is not close to 0. Nowhere close to 0. So again, the immediate impression is what? You will be rejecting H0. The confirmation will come from either p-value or the critical value. So first I will find the F critical value.
So logically, number
This is huge.
closer to infinity.
Logically, if you look at the Z, sorry, not the Z, the F tables, you will see the values, the critical values of F tables are nowhere, none of these are more than 10, 20. So if you are more than 20, the early indication, again, it's the early indication you need to check. For exact, you need to check. So F critical will be what? The value in the F table. So I'm interested in the value, not the probability. So I'll use the F table inversely. So let me check if F distribution is there or not. F inverse is there. What's the lower tail probability? The upper tail should be alpha. Lower tail should be what? I put 1 minus alpha, the lower tail. V1 is K. What is K? 2. V2 is n minus K minus 1. 25 minus 2 minus 1. So the critical value is 3.46. What did I say? Minus 2. The critical value is 3.44 something. Is 244 bigger than that? 261 bigger than that? Of course it is. Which means if you use the critical value approach, you reject H0 at 5%. What if I find the p-value here? The p-value will be upper tail probability more than 261. So now I'll make direct use of F table, not the inverse. So F dot dist. I need the upper tail area, upper than this one. The command will give me the lower tail area, but at the end I will take 1 minus. This will give me upper tail. Degree of freedom for the numerator, 2. Degree of freedom for the denominator, 25 minus 2 minus 1. So the p-value, what is missing? The argument that is missing is cumulative. I put true. What is this cumulative?
Wrong area. Okay.
The answer is forget about this. Always put true. False will give you the height of the curve, and we are never interested in the height of the curve. We are always interested in the area under that point. So for area, you need to put true. If you want the height of the curve, you put false, but we never use false. What is the p-value? 0. What is the meaning of p-value? No, that's not the meaning of p-value. That's the next step. What does this 0 mean? Or let's say this p-value was 0.01. What does 0.01 mean? No, it's not the probability of rejecting H0. P-value, yes.
This happened by coincidence.
The probability that this happens if H0 is true. The probability of getting this big value of F under H0 is 0. If your H0 is actually true, the probability of getting a value of F as big as 261, thus that probability is almost 0. So if that probability is 0, we should not get this value of F, a big value of F if H0 is true, which means indirectly H0 is probably not true. Yes.
This means that this F value will not be. I don't get the interpretation.
The interpretation is if this H0 is true. Where is H0? If this H0 is true, if betas are actually 0, in that case, the getting a value of F as big as 261, the probability of that happening is 0.
And how do we relate that to rejecting this H0?
Because we are saying under this H0, the probability of getting F that big is 0, which means there is no chance of getting F 261 if H0 is true. And we did get F 261.
Okay. But does that mean this is 100% correct? That we should at least one of them.
It's not exactly 0. We are never 100% correct. This is not exactly 0. It is 0.000000 something.
Okay, more than 16. This.
Let me make it bigger. I don't know. It's showing 0. Maybe it's more than 13 decimal places. It's never 0 because the last value in the F is infinity. You never get infinity, so it's not exactly 0. It is 0.00000 many zeros. P-value is never 0. It's never 0. It can be close to 0, but it's never 0. What was the first lecture of the class? The difference between mathematical and statistical relationship. Now, what were you saying? I'll connect it with this one.
I was saying, it's mathematical.
You got it yourself? You got it yourself? Yes. And we are not interested in this. When SSR is exactly equal to SST, this will only happen if all the points are on the line. And that will be a mathematical relationship, not a statistical relationship. There must be some error. In statistical relationship, there will be some error. So that's why when I write here, I write close to and never equal to 0. When I write SSR, I write it approaching 0 and not equal to 0. Any questions at this point? In case of no questions, let us move on to the next topic, which is. And before I go to the next topic, I'll introduce you towards a new term, which is called extra sum of squares. What is this extra sum of squares? This extra sum of squares is a concept which is only related with the multiple regression. It doesn't come in the simple regression. Now, let us say you have this regression. Let us say you have this regression, okay? And let us say you have SST, let's say equals 5,000, and your SSR is, let's say 4,000, and your SSE is obviously what? 1,000, correct? Now, if I add another predictor, what will happen to SSR? It will increase, or it will stay the same. It will not decrease because it's the square. It's the square of the variation explained. So it will not decrease. It may increase, or if x3 is useless, it will not increase. It will stay 5,000, which will give us an indication that the newly added variable is a useless variable. Now, to see the marginal contribution of x3, let us say my SST, will SST change? SST is the total variation in y. It will not change whether you are regressing it on 4 variables or 20 variables. It's still 5,000. SSR is the variation explained by your regression. Before, your regression has 2 predictors. Now it has 3 predictors. This will change, correct? Let us say this new one is 4,100. And accordingly, SSE will be what? 900, correct? What is the contribution of x3? What is the marginal contribution of x3 when x1 and x2 were there in the model? 100. And let's say in percentage, yes, but in absolute terms, it's what? 100. This is called the extra sum of squares brought by the new variable. So we denote it by SSR of x3 given x1 and x2 were already in the model. This is basically SSR of the full regression with x1 and x2. And x3 minus the SSR of x1 and x2. The regression with x1 and x2, it had 5,000, and this one has 5,100. Not 4,000. 4,000. So the marginal contribution of x3 in the presence of x1 and x2 is 100. We're not talking about adjusted. We're talking about before adjustment. This is more closely related to R square, not R square adjusted. Adjusted will come later. This is the spirit of R square adjusted, that R square never decreases. It never tells you a real picture, whether the newly added variable is contributing or not. So that's why we make an adjustment. And this adjusted, we call it R square adjusted, but that will come later. Now this measure, SSR, will tell you the extra sum of squares brought into the regression by new variable, given the old two variables are already in the model.
That wise to use
I would rather not comment on this one. There is a full chapter on this one. There is a full chapter on this one. The evaluation of the regression. How do you evaluate the regression? How do you call the regression a good regression or a bad regression? There are different measures to call a regression a good or bad. So we'll talk about this one. There's a whole chapter. So this extra sum of square concept will be useful when we are testing some coefficients. The case number 3 in this diagram, the one I made for you at the end of the last week, or maybe at the start of this week. So next class, we'll be moving towards case number 3. We are done with testing one coefficient. We are done with testing all coefficients. Next class, we'll be doing testing some coefficients. And next time we'll do the linear constraint thing. Yes. The major? 6 o'clock. Until nobody knows. Nobody knows.
Are you available in your office at 3:30 or 4?
Again?
Are you available in your office at 3:30 or 4?
No, I have a class. From 3:20 to 4:30, I have a class.
So you're not available today?
No, I'll be available in this room. I'll come back. I have a class here.
So